Right, let's get started. So hello everyone, this is SeungryongKim. So maybe this is first lecture after our midterm exam, right? So how was that? How was your midterm exam? Easy or difficult or whatever? No opinion, right? 여러분 어땠어요? 혹시 듣고 계시고 흥미로웠어요? 어려웠다는 소리죠, 그렇죠? 어려웠을 것 같긴 한데. Maybe our final exam will be similar to our midterm exam. So please try to follow the lectures in depth. Okay, albeit difficult. Okay, that's okay because we have a final exam, some presentation and short quiz. So don't worry about your scores. So and let's move to the next topic. Okay, all right. So today we will move to the new topic, visual correspondence. Okay. So before that, any question on our midterm exam? Any question? 자, 여러분 고생했고 우리 중간고사 혹시 뭐 관련해서 질문 하고 싶은 사람 있나요? 없죠? 네. 그럼 우리 이제 시작해 보도록 합시다. So this week and next week we will talk about visual correspondence or image matching. So first of all, what is image matching? Image matching is about the relationship between the source and target image or the multiple images. For example, let's suppose that we have a source images and target images. They taken under the different viewpoint with different viewpoint given a same view, same scene. What I want to do is to estimate where is the same point? Where is the same point between in source and target image like this? So, for example, this is the hand here, and so we have to find out the correspondence here because they are semantically or visually similar region, right? So this is the image matching. In other words, the objective of image matching is to answer which region goes to where. So in this case, so we want to find the correspondence of these patches or this pixel to this pixel, given many candidates, this one and this one and this one, looks like this. The question is which region goes where? This is the image matching goal. Why is image matching is useful? Why is image matching useful? There are so many kinds of application that can benefit from the image matching or the visual correspondence. For example, the 3D construction is one of them. Our next topic will be the 3D computer vision, but as you know, the 3D computer vision, one of the most important issues in the modern deep learning or the computer vision field. So one of the most fundamental technique to reconstruct your 3D model is structure from motion or the MVS or TV stereo, right? So this one is examples of the sparse model of the center loom using the 21K photos produced by the Colmaps SFM pipeline. This red dot represent the camera location and the camera viewpoint if we enlarge this one, and this part point as a 3D model. Or if we densify this 3D model to look like this with the color texture model, we can build the dense model of the looks like this. This is the dense model of the several landmarks produced by the Commerce MVS pipeline. So in this kind of application, the image matching is one of the fundamental steps. Let me show you an example. So this is the general structure from motion pipeline. Given input images taken under different viewpoint and with a different camera or the different illumination setting or the other how to say the other camera setting, something like this. What we want to do, we want to reconstruct a 3D model, static 3D model from here. Structure from motion SFM pipeline consisting of the predictable feature extraction and image matching. This is today's topic, and estimating a camera fold and triangulate the 3D point and bundle them to finally generate the 3D model. So as you can see here, image matching or the feature extraction is one of the most useful or the essential step to understand the geometric relationship between the multiple images. So yeah, this is image matching. So anyway, this is one of the examples of maybe somewhere in Italy. I don't know exactly, but yeah, this is the reconstructed scene by using the SFM. And another example is a SLAM. SLAM. In fact, the SLAM is almost similar to the SFM because their goal are almost the same. So given an input video, looks like this. In SLAM, we want to estimate the camera folds at current frame with sparse 3D model with color point count. So this is the SLAM. So to understand this SLAM, we also have to find out the correspondences between each frame. Looks like this. Other examples is a visual localization, right? So without using any kinds of the hardware-based localization technique, for example, like the GPS or IMU, something like this. Visual localization is only used to the image data to find out your current location with the current camera folds. So why this kind of technique is useful? You can use this visual localization to localize your agent, in this case, the robot or your IoT device, for example, like your smartphone. So here, it's like this. Not only we localize our global region, but also we can reconstruct our camera pose where we see now, which direction we follow now. Looks like this. So it has so many kinds of useful. For example, the visual navigation, something like this. So in this case, the matching or the correspondence is fundamental step. What else? Augmented reality or the virtual reality. For example, most of you already very well knowing the Pokemon Go, which was the augmented reality devices or the application. So in this case, we have to find the correspondences between the real scene. This is going to be the images and the virtual 3D world. Or virtual reality or the mixed reality or the panorama stitching, right? So to build these single images given from multiple images, we have to find out where this point is corresponding to the here, or this one is to here, here. Then we can generate the panoramically stitched images. What else? Tracking the object from those first frame to the remaining frames. So yeah, that's another application. Anyway, there are so many kinds of application to use that can use the image matching. So in other words, the matching set of the images enables us to recover the geometry of the world from the individual images. So here's the example. Given the same scene, looks like this. If we take this scene with 3 different camera or under 3 different viewpoints, maybe we can achieve the scene A, scene B, and scene C. Matching a set of the images, matching scene A and B, and matching scene A and C, then we can recover the camera motion from A to B, A to B, and A to C, A to C. So that's why these kinds of technique can be used to reconstruct your 3D model or your 3D geometry field. So image matching enables us to recover the geometry of the world from the individual scene. Why? Why? So if we see detail, right? So let's say this is a real scene, and let's suppose that we have a 2 camera. Take a left view and right view. So camera 1, camera 2. Then let's suppose that here's the one point in the left images or left view, and here are 4 kinds of points on the right view here. Then if we draw the line from left view images and right view images, looks like this. If real point was here, these images, this pixel in the right image should be same appearance to this point. In other words, if we can achieve this one is similar to this one, then we can reversibly recover the real 3D point, real 3D point on the real world. So this kinds of techniques called the point triangulation to extract the 3D information. Yeah. So this is the point this is the using point correspondences for the triangulation to recover the 3D information. In fact, one left view to right view match is not enough to recover the precise 3D model. So mean number of the matches define the theory and algorithm. For example, 8-point algorithm. Practically, we aim to higher number of the matches than the theoretically. So, in other words, to understand camera pose variation between the left view and right view, we need at least 8-point correspondences. But in practically, we aim to find or establish higher number of matches than theoretical. For example, the larger than 100. So, yeah, that's one of the way to use the correspondence, the images, corresponding pixels to recover the 3D or the camera pose. Then how can you do that? How can we find out correspondence? Classical image matching pipeline follow the 3 steps: detection, description, and matches. Detection, description, matches. In step 1, in detection step, we have to choose interesting point. So interesting point means looks like this. Okay. So as you can see here, image 1 and image 2, if we choose one point here in the homogeneous region or the textual region, this one may not be established one-to-one mapping, right? So in feature detection step, we have to find out repeatable point, looks like corner point, like this. So this is the feature detection step. And feature description step, we have to convert the point to the suitable mathematical representation. In this case, just the descriptor or the vector, maybe only the vector. For example, let's suppose that we detect the point here. Then we have to describe this local region as a 1D vector. Looks like this. It should be similar to the corresponding feature vector, while it should be dissimilar to the non-correspondence region. For example, like the negative regions. This is a feature description step. In step 3, matching step, we have to match the point descriptor between the two images. One of the most simplest way to find out matches given the n feature vector and m feature vector in left and right images respectively. One of the simplest one is find out m by m matrix, similarity matrix, but it may be so we usually use the optimization or the other context injection technique to improve the matching task here. Anyway, this is the classical pipeline for the image matching task. Among them, scale invariant feature transform, which was called shift, is the pioneer work for the image matching task. This paper summarized this previous pipeline for the image matching. So their goal is similar. Given two images, looks like this. Then we want to find the correspondence like this. Then first, how can they do? Given image 1 and image 2, first of all, for each images, they extract the feature vector, feature point, and orientation of each pixel. So in this case, if we enlarge this part, this one, so main orientation, and then they describe the local region, I mean the nearby region, as a feature vector. For example, 128 by 1 vector, something like this. Then do the matching. So this is the fundamental steps in SIFT, or the conventional image matching task. As you know, maybe as you know, the SIFT, this scale invariant feature transform, was the most cited computer vision paper ever before the deep learning revolution. But after the deep learning evolution, AlexNet or the LastNet, VGNet overcome this number of citation of the SIFT paper. But at the time, before the deep learning revolution, SIFT paper is the most cited computer vision paper ever. So that's proved the that's proved the importance of the image matching in the computer vision application. Anyway, after deep learning revolution, this paper is the number of citations decreased slightly, but anyway, even in modern computer vision field, this SIFT paper definitely affect on so many kinds of papers and image matching paper. Anyway, this is a SIFT paper. 자, 오늘 좀 많이 왔는데, 자, 이제 우리가 한 번만 한국말로 정리하고 가면, 이제 이번 주 다음 주에 이미지 매칭에 대해서 얘기하고 있어요. 그래서 뭐 앞에 쭉 얘기했지만 이미지 매칭이라고 하는 게 이제 뭐냐, 그렇죠? 뭐 너무 간단하죠. 이미지 매칭은 동일한 점을 찾는 문제예요. 멀티플 이미지에서 which relations goes where, right? 근데 이제 너무나 이게 왜 필요하냐, 너무 많은 곳에 쓰일 수 있다라는 거예요. 대표적인 3D 리컨스트럭션 파트. 뭐 요즘에 이제 우리가 현대 3D는 사실 모노큘러 이미지로 많이 가요. 그러니까 싱글 이미지를 가지고 3D 리컨으로 많이 가지만 기본적인 3D 리컨스트럭션은 어떤 지오메트리, 그러니까 피직스 베이스죠. 지오메트리컬하게 디퍼런트한 뷰포인트에 찍은 영상들을 가지고 리컨한 3D 정보를 얻어내는 거였는데, 이제 그때 사실 가장 중요하게 사용되는 게 바로 이미지 매칭. 멀티플 이미지들 간의 릴레이션십, 지오메트리컬 릴레이션십을 찾아내는 과정이고요. 뭐 SLAM, 비주얼 로컬라이제이션 중에 뭐 아그멘티브 러닝, 스티치 뭐 너무 많이 쓸 수 있고 왜 중요하느냐? 결국에 matching a set of images는 geometry, 월드의 지오메트리를 리커버할 수 있다라는 점 때문이죠. 그렇죠? 왜 그렇냐? 이걸 설명을 했죠. 어떤 리얼씬을 우리가 두 장의 카메라 찍었을 때 이미지 위에서의 동일한 점은 결국에 어떤 3D, 그러니까 리얼 월드에서의 어떤 점에 어디에 위치했는지와 바로 다이렉트하게 연관이 되어 있기 때문에 바로 이 3D 정보와 이 카메라 포즈의 디퍼런스를 베리에이션을 알 수가 있다는 점이었고요. 어떻게 하느냐? 디텍션, 디스크립션, 매칭이라는 3스텝으로 이루어져 있고 어떤 논문들이건 간에 이 스텝을 따라간다. 그래서 현대의 어떤 이미지 매칭 논문도 이 스텝으로부터 자유롭지 못하고 이 스텝을 어떻게 해결했느냐가 결국에 현대의 이미지 매칭 논문들까지도 영향을 받고 있다. 그런 측면에서 이러한 시프트 페이퍼가 정말 의미가 있었던 페이퍼였고 이미지 매칭이라고 하는 개념을 정립했던 페이퍼였고 이게 사실 딥러닝 전 시대에 가장 많이 사이테이션이 됐던 페이퍼였기도 하고요. 사실 제가 박사를 시작했을 때 가장 먼저 시작했던 연구 분야 그리고 지금까지 했던 연구 분야가 바로 사실 이미지 매칭이기도 합니다. Anyway, so this is the shift paper. Question. Question. No? Okay. So, in fact, in our previous lecture, we started from the deep learning based model, but today I would like to start from the shift paper, even though this is the handcrafted model, because after that, after deep learning revolution in image matching field, many researchers try to reformulate this shift paper in a end-to-end manner or the deep learning within the deep learning model. So that's why we have to know the shift paper. So shift paper consists of the local feature detection step, and main orientation, estimation step, and feature description step. So let me show you from the feature detection step. So first of all, how they find the feature point? They use Gaussian scale space. This is just the multi-scale images. This is original images, and this is the low resolution images. Also this GSS or Gaussian scale space is produced by directly conforming the last layer images with the Gaussian kernel. This is very simple now, right? But at the time, it was the revolutionary technique, and it gives so many inspiration to the many paper. For example, as you know, feature pyramid network, right? In object detection model, so many kinds of paper inspired by these kinds of multi-scale images. It also used this scale space theory, and they view the different of the scale space, which is called the TOG, by subtracting the neighboring GSS layer, Gaussian scale space layer, and they use these images as a score map to determine feature point. Why? It is based on the scale space theory paper in 1994. Was very old in IJCB. It's not IJCB. Journal of Applied Statistics. And the Professor Lindeberg shows that the normalization of the Laplacian is required for the true scale invariance. And later, the Mikulasky found the maximum and minimum of the Laplacian Gaussian produced the most table mean features, blah, 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 blah. And anyway, they found that this kind of difference of the Gaussian model, the difference of scale space images can be used to localize the feature point. So, looks like this. So, given an image, we first made a scale pyramid by convolving the convolutional, by convolving the Gaussian kernel and find the difference between them, just difference, and find the extreme point here. Then by accumulating this point to the original image again, then we can finally determine the feature point. So how in this paper they use the non-maximal suppression, which is called NMS, which is almost similar to the NMS in the object detection model. So maybe they use the same idea from this CVT paper. Anyway, how they do that? This is the difference of the scale space images, and they search the extrema by considering the 3 by 3 by 3 tensor local tensor, and find out and determine the center pixel is the maximum or maximum point. Then check this is the extreme or not, extrema or not. Then we localize the key point or the feature point. And next step, we compute the dominant orientation for each pixel, for each this feature point. How can we do that? First of all, compute the orientation histogram. This is just like gradient. Histogram of the gradient orientation of the nearby pixel, and fill the histogram looks like this, and just pick the most frequently selected object orientation, and here, from here, we decide the main orientation. And then this main orientation is to use to localize near neighborhood information, which is used to describe this local region as a feature vector, right? So this is a dominant orientation step, which help to give rotation invariance to the model. So from this scale space theorem, scale space based detection, we achieve scale invariance, and from dominant orientation estimation module, we achieve the rotation invariance. And then we want to describe this region as a 1D vector. Then they use gradient magnitude and orientation again to describe the feature vector. How? First of all, just to compute the gradient. This is just image gradient and Gaussian weighting function. To avoid the subtle change in the descriptor within the small chain, it means just apply the Gaussian noise, Gaussian function looks like this, and then generate the histogram. But before that, divide each neighborhood to the local region and quantize the orientation. Quantize orientation and generate the histogram. So which is going to be the 128 dimensional vector. Looks like this. And finally, feature vector normalization used to reduce the effect of the illumination chain. So through this kind of pipeline, FIF2 algorithm achieve square invariance, rotation invariance, and illumination invariance. So this is the result of the fifth paper. At the time, they just used the graphical images and very low resolution. And at the time, there was no neural network and things, but interestingly, the performance was very impressive. So they show this image matching technique can be used to object recognition in clustered environment. Looks like this. So here is the input images, and this is another images, if we can find the correspondence between two images, for example, this one corresponds to here, this one corresponds to here, this one corresponds to here, then we can localize a new object here or here, maybe this one. Then there is an object like this. And if we change other clutter, other template, and we find out other object regions. This is one of the technique to find out the object, to find the object region using the image matching technique. And they show that the quality of the float is not very good, but the performance was very intuitive, impressive. They empirically found to have a good performance under the range of transformation, for example, rotation, scale, intensity change, and small affinity transformation. Like this. Anyway, it was the fifth paper. Fifth for the visual recognition. Even though this fifth paper is developed for the image matching or the liquid feature detection and description, after that, this method is to use the global feature vector estimation by using the bag of word or the bag of visual word. How they do that? For example, extract the feature vector, local feature vectors from the input images, and they just encode to the code book and using the pooling and make a global feature vector for each images and use the classification or else. So before the deep learning revolution, before the AAA739, the shift descriptor based back of word technique was the SOTA, SIFR in 2011. Even though, but after AAA739, everything is changed, but CNN consisting of the sequential layer from small layer to the let me show you example. CNN model consisting of the local layer or the coarse layer to the fine layer or the local layer to the deep shallow layer to the deep layer, blah blah blah. And this bag of word consisting of the shift, which is local feature, and the bag of word, blah blah blah. So this pipeline is different, definitely different, but this philosophy is exactly similar to the previous method, shift plus bag of word. Anyway, nowadays, so CNN or transform is so top, but the philosophy of this feature description start from this handcrafted model. 그래서 이런 제가 이제 이번 강의에 이제 대부분은 핸드크래프트 얘기는 안 하고 있어요, 사실. 그렇죠? 근데 이 논문은 꼭 얘기하고 싶었던 이유가 많은 이제 의미를 가지고 있는 논문이었고, 이미지 매칭만 봐더라도 이제 이미지 매칭에 지금까지 나온 논문들이 이 시프트 방법으로 어떻게 잘 리포뮬레이션하고 그 시프트에서 만들어냈던 그 파이프라인, 디텍션, 디스크립션 이거를 어떻게 잘 따라가고 하는 것들에 대한 연구이었던 걸 보면 정말 의미가 있는 연구였고, 시에나 트랜스포머가 어떤 로우 레벨 투 하이 레벨 피처 익스트랙션 한다라는 관점에서 시프트를 통해서 백업월드를 했던 거가 로컬 피처죠, 시프트가. 그다음에 백업월드가 그걸 어그레이션 하는 거니까 하이 레벨 피처라고 볼 수 있는데, 어떤 그러한 필로소피가 이런 딥 레이어를 만들어가는 데 많은 영감을 준 논문이기 때문에 제가 조금 시간을 할애해서 설명을 해줬고요. 이거 끝나고 이제 조금 한번 제가 더 얘기를 하고 싶었던 얘기가 있어가지고 좀 더 시간을 써보면, 이거 오프 더 레코드까지는 아니고 좀 더 얘기를 해주면 이런 좀 재밌는 일화가 있어요. 시프트라고 하는 페이퍼가 ICCV 알죠? 여러분, ICCV 우리가 아는 그 ICCV예요. 1999년도 ICCV에서 논문이 발표가 되었고, ICCV에서 2004년도에 저널 버전으로 바뀌었어요. 그렇죠? 그래서 이 논문은 이 데이비드 로에, 지금 생각이 안 나는데 교수님이세요. 어디 학교 교수님이시고 그 구글에 지금 같이 겸임 교수로 계시는 이제 로에 교수님께서 단독 저자로 ICCV의 논문을 쓰셨고 이제 ICCV로 확장했던 논문인데 너무나 재밌는 일화가 제가 얘기했지만 시프트 페이퍼가 사실 컴퓨터 비전 역사상 딥러닝 전에 사실 가장 많이 사이테이션된 페이퍼였어요. 물론 이제 바뀌었죠. 지금은 레슨넷이겠죠? 그쵸? 지금 레슨넷이 아마 제일 사이트 많이 됐을 것 같은데 한번 찾아봐요. 네, 그렇게 의미 있었고 이렇게 많은 현재까지 영향을 주던 페이퍼임에 확실한데 이 당시 물론 저도 이 당시는 연구를 안 하고 있었으니까 들었던 얘기가 ICCV 학회장 가면 지금처럼 막 이렇게 포스터가 있었겠죠? 이 시프트 페이퍼가 그 포스터 중에 가장 구석대기 자리에 배정을 받았다고 해요. 그래서 사실 사람도 한 명도 오지 않고 소위 말해 파리가 날리는 그런 논문이었다고 해요. 그렇죠? 뭐 그때까지만 이 가치를 몰랐던 거죠, 사람들이. 근데 이제 세월이 지나고 이게 저널 버전 나오고 사람들이 실제 써보니까 일단 정말 잘 되고 진짜 의미가 있는 페이퍼임을 알고 점점점 사이테이션이 되더니 이제 세상을 바꾼 페이퍼 중에 하나로 이제는 우리가 알고 있고 제가 지금 여러분들 가르치고 있는 페이퍼까지 된 거죠. 그렇죠? 너무나 큰 의미가 있는 거죠. 뭐 물론 뭐 진짜 요즘에 유명한 논문들은 나오자마자 막 아카이브 올라가자마자 대박이 나지만 그러지 않을 수도 있다. 여러분들 하는 많은 연구들이 뭐 대부분들은 역사 속으로 사라지겠지만 솔직한 말로 무조건 그런 건 아니다. 여러분이 정말 의미 있는 연구를 했다면 언젠간 사람들 그 가치를 인정해 줄 거다. 라는 얘기 좀 해주고 싶어서 그렇죠? 그래서 너무 일일비하지 마라. 를 얘기해 싶어서 좀 시프트라는 페이퍼를 좀 준비해 봤습니다. 알겠죠? 자, 우리 빨리 딥러닝으로 넘어가야 되니까 좀 넘어갑시다. So, it was a shift, but after deep learning evolution, there was so many kinds of deep neural network-based methods to solve the image matching problem. But before that, before 2012, there was the one method that used a neural network. It was not a deep neural network, but just a convolution neural network to describe the feature vector. Looks like this. So given a two patches means this one from the one images and maybe this patches to the other images. Then we want to find out, we want to determine these two patches similar or not, right? And in 2008, there was the one attempt to formulate this similarity function between two patches as a neural network, but the performance was very, very limited compared to the fifth paper, so it was not achieved the many it was not received the other spotlight or whatever, but it was the first attempt to use a neural network. But anyway, after deep learning evolution, many researchers tried to formulate deep neural network-based image matching model. The first deep success was this paper, Discrete Matching with the convolutional neural network, comparison to the SIFT in 2014. What they want to do, right? So if we have the pre-trained image classifier pre-trained model, then if we removing some remaining part, we can achieve the backbone feature in terms of the feature vector. Looks like this. Then maybe we can use this one vector as a local feature vector similar to the SIFT, and we can find out correspondences between this feature vector, right? Local feature vector. And in other words, they get network pre-trained on the ImageNet and remove the abstraction layer and use that feature vector to solve the image matching. And performance was not so impressive, but they first showed that convolutional neural network can be the alternative solution to solve the image matching problem. Then after that, many researchers try to formulate deep learned descriptor, not a handcraft descriptor such as the SIF, but they want to formulate deep learned descriptor. How they do that? Given two images, first they extract the picture patches, input patches, and enlarge these patches and try to learning neural network to say these two patches is similar or dissimilar or matching or non matching. Then we can solve image matching problem with a deep neural network. So this is the general idea of the deep learned descriptor. So deep compare paper was the starting point for this image matching in a deep learning. So core idea of this deep compare paper is use CNN plus metering network to learn a similarity function for a pairs of the patches. Ideas like this. Given a patches, two patches, patch 1 and patch 2, we want to determine the similarity between these two patches, and they try to formulate the convolutional neural network with a decision network and want to learn this network with triplet loss, or the metric loss. How? We just make positive patches with labels and negative patches with the zero label, and by using this kind of training data, we can train this network, right? So this is the first idea. And first of all, they use this kind of loss function. This loss function is very, very simple. For the level 1 matched point, this one, output of the network should be 1 if yi, the label, is 0. The output of the network should be 0. So it can estimate similarity or dissimilarity. And how to design the convolutional neural network here. In this paper, they propose three kinds of one: two-channel network, CMS network, or two-channel two-stream network. So two-channel network, two-channel version is very, very simple. Let me show here. They just first in this architecture, they just to concat patch 1 and patch 2 and feed forward these two patches to the network and use the decision network. This is just FC layer, and estimate the similarity of these two patches, and no direct notion of descriptor, because they just concat and simply consider the two patches of the input pairs of two-channel images. And maybe this is computation expensive. Pairwise separation cannot use the descriptor of each patches. It means that, right? So if we have the two images and there are n by m patches, then this network require n by m feed forwarding process to find the correspondences. So this is one of the example. And the next paper was the CMS architecture. How they do that? First of all, they extract the independent feature vector from the independently defined two patches with a shared network. And this is just the descriptor, CMS feature descriptor. And then they used additional decision network, which is called the metering network, to determine similarity. Another network, they try to consider the different context information. So for the current pixel value, they extract the these patches and these patches, and this network compare the low level of the smaller scale similarity. This large scale similarity, and this one comparing the small scale similarity because the this one is smaller, right? And then decide the similarity with the distant attribute. Yeah, so this kind of technique allows the network to process at the two different resolutions here. So this is the T-compare paper in CBPR 2015. Any question? Any question? 따라올 만하죠, 여러분? 할만하죠? Question? No? Okay. So after that, I'm in the similar time. Maybe at the maybe Comfortability as a Comfortability in ICCB 2000 이게 전에 나왔는데 2014 때 나왔을 건데 in archive there was a deep disk paper, and comparing to the previous T-compare, they want to use Euclidean distance to define the similarity between the two patches. How they do that? They want to formulate direct substitution of the sieved paper from the two patches, patch 1 and patch 2, with a CNN architecture, with a shared one. They extract the feature vector, tx1 and tx2. This is 128 dimensional vector, and just to compare just measure the similarity with the dot product or the L2 norm, and try to train this CNN architecture. If we successfully train this kind of CNN architecture, then we can directly, it can be directly substitution of a shift. Then the application of this kind of discrete may be infinitely many. And how to learn this network? The learning loss function is similar to the previous one, and we already have the ground truth. These two patches are similar or not. We already have the ground truth training data. So we define the loss function to minimize the pairwise hinge loss. For the positive sample, we try to minimize the distance. If this is the negative sample, we have to maximize the similarity. Then this descriptor model, CNN architecture, can generate the better feature vector based on the learning signal, right? This is a deep descriptor. How do we design this CNN model? Looks like this. From the 64 by 64 images, we want to extract the 128 dimensional feature vector. How can you do that? They first of all use the 7 by 7 by 32 by 64 and pooling, normalization, pooling, normalization, blah blah blah, and then generate the 128 dimensional feature vector. It was a 3 commotion layer. It was very shallow one, but performance was not bad, right? So it achieved the better performance comparing to the SIFT at the time. And one more thing is that this paper proposed the hard negative mining technique to train this kind of matching learning technique. So where did we discuss this hard negative mining? In contrast learning이었죠? 우리 contrastive learning에서 나오던 그 네거티브 마이닝이 결국 여기서 또 똑같이 썼던 거죠. To alleviate the probably imbalanced positive negative samples, and which was the key to the good performance from here. So what does it mean? So this is the training data. This blue the blue dot means same positive sample, and different color means negative sample. And if we define group pairwise the similarity to as a loss function, it should be this one, this one, this one, and this red arrow will be the negative sample, and blue line means the positive sample. But this is the brute force way. But as we discussed in object detection as a focal length, considering whole possible signal, it's not a good solution. I mean, optimal solution. And hard pairs mean just consider the few sample which was hard to determine positive and negative. So they propose this kind of hard negative mining. I will skip the detail, but if we use the hard negative mining technique, so this is the brute force way without any hard negative mining. But with the hard negative mining, we can drastically improve the performance, even double scores at some degree, at some setting. So from here to here. So this is hard negative mining to train the convolutional neural network for the image matching. It was the deep disk question. No? Okay, so yeah, so it was the deep disk. After that, we will see the many other improved version and people that one time. Okay, so let me take a 10-minute and a 10-minute break, and let's see again 3, 2 p.m. Okay, 10분 쉬었다가 우리 3시 2분에 다시 봅시다. All right, let's continue. Question so far. Nope. Okay. So after this paper, there was another paper learning local feature descriptor with a triple loss and shallow convolution network. So idea is very similar, but core idea was this paper was that smallest negative distance between the triplet should be larger than positive distance. So in this paper, given x, y, g, and with a network, and we extract the feature vector, dx, dy, and dg, and is dx more similar to the dy than dg? So they formulate this kind of philosophy as a triple loss. There are several kinds of triple loss. For example, ranking based method and ratio based method. And it's very simple. We'll skip this one, but main idea is that this one similarity between the positive sample should be increased and the similarity between the other sample should be decreased with a single loss function. So this is a triple learning based image matching, image descriptor learning technique. So far we discussed the descriptor learning technique for the image matching. And after that, one of the paper tried to solve the other part. In this case, the object dominant orientation alignment problem, learning to assign the dominant orientation. How they do that? So this is the dominant gradient orientation assignment based method. For example, shift one, and this is the learned orientation. And compared to the shift based shift orientation estimation method, based on the gradient histogram of the gradient orientation. In this paper, they try to learn the even orientation. How? So we already know this one and these patches are similar one. Then using the orientation estimation network, try to generate the dominant orientation, then normalize to the same direction and extract the picture vector and define the matching loss function. For example, like the shift or the deep disk, whatever. And by backpropagating the loss gradient to the orientation estimation, we can find out good orientation for the image matching task. So this simple baseline shows that improve the result with good orientation estimation. So yeah, with different backbone picture vector with orientation estimation technique, we highly boost the performance. This is the learning to assign orientation. Use the CBPR 2016 paper. And after that, there was another paper, LIFT, Learned Invariant Feature Transform, which was called LIFT. So from the title, we can easily imagine that this paper tried to resemble the SIFT as much as they can. This is the first end-to-end feature detection and description model by reformulating the SIFT paper in a deep learning based technique. Looks like this. So this is a shift pipeline, local feature detection and orientation estimation and feature description, and they formulate detection model, feature detection model, orientation estimation model, descriptor estimation model. For example, deep disk. Then they try to learn in an end-to-end manner. And after that, given a dispatch, this lift pipeline generates the discrete vector, something like 128, similar to the shift. Then, how to train this network? They proposed a quadruplet CMS network, not a triplet anymore. Quadruplet CMS network. In this paper, they also consider the positive samples and negative sample, but they also additionally consider the non-key point. It's not a key point anymore. It's just like the homogeneous region or the tactile region. Then try to describe the feature vector sequentially and through the proposed lift network, and try to train the model between to maximize the similarity between the T1 and T2 and minimize the similarity between the T1 and T3. So this is the learning pipeline in the lift paper. We will skip this network architecture, DET, and orientation estimation, deep disk. But at testing time, similar to the scale space, they build the scale space images in testing time only, and detection, and build the scale pyramid, and using the notation suppression similar to the scale seed, extract the key point or the feature point, and crop the each patches and estimate the orientation, and normalize the orientation and describe the feature vector and do the matching. So this is the pipeline for the lift paper. So use the first paper to formulate the lift paper in an end-to-end manner. What else? There are other paper called Superpoint. Let's skip this paper. It's not important. Let's skip Superpoint. And there was the T2NAP. And idea of T2NAP is also very interesting. Previous CNN or the lift paper, previous shift or the lift paper philosophy is like that. Detection. First, detect the feature point. Okay, this is image using the CNN or the Gaussian pyramid model. Detect the point and describe the feature vector with the CNN or the gradient orientation, something like this. So detection, then description. But in this paper, in T2NAP, they formulate detection and description formulation. So in other words, they try to detect the both detect the point and description with a single network. This is a T2NAP. T10 use a single CNN model which extracts the depth features that serve as both descriptors and detectors. So this is a T2NAP. How they do that? Looks like this. So similar to the other CNN-based model, given an input image, first extract the feature vector, the feature tensor. So it should be H by W by N. N is the dimension of the feature vector. And we already know each feature vector at each point, each pixel, act like a local descriptor, right? And one of the things we have to consider is how to select among them, right? And in this paper, they propose a soft detection module. Soft detection module means using feature values itself as a score map to detect the feature vector. In other words, by considering this tensor itself as a score map, and using the no-measure separation like this, we just extract the extreme point, which is going to be the feature point, and we already know the discrete term at this point. Then we can say that we jointly detect and discrete. We jointly detect and describe the feature point. So this is a T2 In other words, local descriptors are simply obtained by traversing the whole feature map as special position, like this. And detectors are obtained by performing non-local maximum suppression on the feature map, similar to the SIFT. This is the T2 map. Question. 오늘 뭐 질문이 현저하게 줄었는데 어렵나요? 따라올 만해요, 여러분? 지금 열심히 듣고 있는 친구들 중에 혹시 따라올 만한가요? 어때요? 어렵나요? 쉽나요? 어려워요? 그렇구나. 오케이. 다 어렵구나. 어디서부터가 좀 어려워요? 그러니까 제가 좀 빨리 넘어가는 페이퍼들은 그 디테일들보다 좀 하이 레벨을 여러분들이 이해했으면 좋겠어서 좀 빨리 넘어가는 거긴 한데, 뭐 디텍션 요 파트나 요런 부분들이 조금 설명을 더 하면 좋은데 요런 거까지 설명 너무 길어질 것 같아요. 제가 넘어가고 있긴 한데 혹시 하이 레벨은 이해가 되나요? 좀 어렵구나. 좀 그러면 의견을 줘볼래요? 어디 부분이 어려워요? 어떤 부분들이 좀 이해가 안 되는지 좀 설명을 해주면은 제가 좀 더 설명하는 도움이 될 것 같은데 어떤 부분이 잘 이해가 안 돼요? 겨냥하는 포인트? 겨냥하는 포인트는 이거예요. 요거. 결국 어떤 두 개의 패치가 들어올 때 두 개의 패치 사이의 시뮬러리티를 어떻게 재느냐에 대한 연구들이 이제 디스크립터 관련된 연구들이고 이젠 그거는 아까 제가 처음 얘기했던 원래 이미지 매칭 파이프라인 중에 사실 여기 이 디스크립터 쪽만 사실 고려한 논문이고 아까 리프트라고 하는 논문 런드 인페런트 피처 트랜스폼 같은 논문은 이 부분, 이 전체 디텍션부터 매치까지 가는 엔드 투 엔드를 다 딥런을 바꿔보는 파이프라인을 보여주시면 되고요. 준영 학생. 요 패치를 뽑는 방법은 사실 다양해요. 만약에 우리가 시프트로 뽑는다 하면 시프트 아까 쭉쭉쭉 뽑는 방법처럼 시프트로 뭐 스케일 스페이스 만들어가지고 막 이렇게 해가지고 뭐 익스트림하게 딱 찾아가지고 그냥 요 점들을 뽑아내는 게 가장 일반적인 거고 이제 뭐 요걸 뽑는 다른 방법들도 막 나오긴 했는데 시프트가 가장 대표적이었고 이 리프트 같은 경우는 이걸 그냥 제가 그냥 넘어가면 어떻게 하냐면 봐요. 어쨌든 이 스코어 맵이 있으면 스코어 맵이 뭐 별게 아니라 그냥 이미지예요. 이미지 스코어 맵이 있으면 이 스코어 맵에서 봐봐요. 이 스코어 맵이 있으면 이 스코어 맵에서 맥시멈이 되는 점 그렇죠? 맥시멈이 되는 탑 몇 개를 뽑아내면 그게 이제 포인트들이 되는 거죠. 그렇죠? 그렇게 뽑아낸다고 보면 돼요. 그걸 하는 방법 중에 하나가 시프트였던 거고 러닝 기반으로 가면 그냥 그거를 디텍션으로 이렇게 뽑아내는 거고 그렇죠? 유기용 학생 자, 너무 정확한 포인트 컨트롤 러닝과 똑같아요. 제가 얘기했잖아요. 컨트롤 러닝 설명 똑같죠. 컨트라스트 러닝이 나왔던 것 자체가 이 매트릭 러닝부터 나왔어요. 사실. 오케이? 그래서 말했지만 제가 막 로스들이 막 설명하는 게 결국에 제가 얘기했던 거 비슷한 걸 비슷하게 먼 걸 멀어지게 하는 러스 펑션 사실 정말 많아요. 그렇죠? 뭐 이렇게 줄 수도 있고요. 그렇죠? 아니면 이렇게 줄 수도 있고요. 그렇죠? 뭐 이렇게 줄 수도 있고요. 그렇죠? 많은 연구들이 사람들이 해왔겠죠. 근데 그러다가 info and see loss라고 하는 게 매트릭 러닝 중에서 이제는 활발히 연구되었고 그게 이제 바로 셀프 스파이 러닝에서 컨트롤 러닝 쪽으로 넘어온 거다 라고 얘기를 했었고 이거는 그 전에 역사 얘기를 좀 하고 있는 거예요. 컨트롤 러닝 인포 and see loss 나오기 전에 러스들 하지만 똑같아요. 그쵸? 큰 필로소피는 다 똑같은 거죠. 그쵸? 그렇구나. 누구한테 물어볼까? 정은 어디가 좀 어려워요? 랑 다현 학생, 유진 학생, 그 다음에 누가 있었더라? 준영 학생 아까 물어봤던 것 같고. 우리 조금 시간이 있으니까 조금 얘기를 해보고 갑시다. 어떤 부분이 좀 어려운지 여러분 제가 알면 조금 뒷부분 설명할 때 도움이 될 것 같아서 어떤 부분이 좀 이해가 안 가죠? 전부 다? 전부 다나요? 그쵸. 보서 학생 얘기부터 해볼까요? 아까 태스크 자체가 그쵸? 태스크 자체 이건 뭐 그냥 태스크 자체가 결국에 이게 사실 이 페이지를 이해하면은 다 이해할 수 있어요. 사실 이 페이지를 이해하면 다 이해할 수 있고 자 이렇게 정학생 질문과 비슷한데 다시 한번 얘기를 해봅시다. 자 태스크를 이해하는 거 오케이. 자 이미지 매칭이 왜 필요한지는 얘기했죠? 그렇죠? 아까 얘기했지만 이미지 매칭을 하는 건 결국에 이 이미지 두 장의 이미지 또는 멀티플 이미지 사이에 동일한 점을 찾는 문제예요. 그건 이해했죠? 그렇죠? 얘가 얘랑 동일하다. 얘가 얘랑 동일하다. 얘가 얘랑 동일하다를 찾는 게 이미지 매칭 문제예요. 그렇죠? 뭐 그게 왜 필요한지는 막 얘기를 했었고, 그렇죠? 그럼 결국에 뭐냐? 이걸 어떻게 할 거냐? 그걸 하려면 뭘 해야 되냐면 첫 번째 어느 점을 찾아야 될지를 이렇게 포인트를 뽑아야 돼요. 그렇죠? 이 지금 초록색 포인트들이 어느 점을 매칭을 할지 찾은 거예요, 지금. 어떻게 움직이지? 네. 아이고. 이 점들이 두 장 영상에서 초록색 점들이 첫 번째 디텍션, 그러니까 피처 디텍션은 어느 점들을 뽑아야 되는지를 찾아낸 거고, 그렇죠? 그 다음에 그 점을 요렇게, 아이고, 죄송합니다, 이게 잘 안 되네. 그 점을 이렇게 그 벡터로 표현한 거고, 자, 얘가 n기압표였고 얘가 m기압표였으면은 그 디멘전이 만약에 d 디멘전이면 n by d랑 m by d가 있는 거죠, 그렇죠? 그 다음에 뭐예요? 그냥 그 시밀러한 거. 그러니까 이게 어렵게 생각하지 말고 그냥 이 패치들이 그냥 각각 이미지로 생각하면 돼요. 그렇죠? 그래서 n개랑 m개의 이미지 간 시밀러리티 가장 높은 애를 찾아내면 그게 매칭이 되는 거죠. 그렇죠? 그래서 그거라는 파이프라인. 그래서 결국에 우리는 두 장의 영상에서 어느 점들이 대응되느냐를 찾는 과정이 매칭인 거고 그게 이제 디스크립션과 디텍션과 디스크립션을 나눈다 라고 이해할 수가 있을 것 같아요. 자, 정은 학생 질문 좀 넘어가 보면 오리엔테이션이 그래서 결국 뭐냐? 그거 어떻게 하지? 오른쪽 어떻게 하지? 됐다. 이거예요. 자, 노란색의 중점이 우리가 디텍션한 포인트예요. 픽셀 위치. 근데 그걸 디스크립션 하려고 하면 그 주변부를 보고 피처 벡터를 뽑아내죠. 그러니까 우리가 CNN 돌릴 리셋 필드가 가지고 피처 벡터 뽑아내는 거랑 똑같이. 그렇죠? 근데 그 노란색 주변으로 피처를 뽑을 때 이렇게 그냥 업라이트된 이 렉탱글 네모를 잡아서 뽑을 거냐? 그거보다 이렇게 얘가 어떤 로테이션을 가지는지 얘가 어떤 방향을 가지는지 이 픽셀이 가지는 어떤 메인한 디렉션을 찾아서 고길 주변으로 이렇게 잡으면 로테이션의 인베런스를 줄 수 있다는 거죠. 왜 그러냐? 이런 걸 생각해보면 돼요. 여긴 못 그리는구나. 이렇게 그리면 돼요. 뭐냐면 왜 그러냐면 이런 거예요. 영상에 두 장이 있어요. 사람이 이렇게 생겼어요. 그쵸? 오케이? 자, 얘를 디스크립션 하는 것과 얘를 디스크립션 잘해야 이 두 개가 같다는 걸 알아야 되는 거잖아요. 그쵸? 근데 지금 보면 얼굴이 돌아가 있어요. 이렇게. 그럼 결국에 똑같은 걸로 피처를 뽑으면 조금씩 값이 달라질 거잖아요. 그렇죠? 그러니까 얘를 이렇게 뽑히고 이렇게 뽑히면 제일 베스트일 거예요. 그러면 디스크립션 하면 거의 똑같이 나오겠죠. 그때 그 디렉션. 그럼 얘 디렉션은 여기고 얘가 디렉션이 여기다. 라는 걸 찾고 싶은 거예요. 그래서 이렇게 돌려서 뽑아야 로테이션 인베리언스하게. 로테이션 인베리언스가 뭐예요? 그러니까 내가 찍었던 영상이 로테이션이 들어가도 동일한 피처 벡터를 뱉어내야 된다. 라는 걸 줄 수 있다는 거죠. 로테이션 인베리언스. 그렇죠? 그래서 이 디렉션을 어떻게 찾을까가 도미넌트 오리엔테이션 에스티메이션이라고 하는 건데 도미넌트 오리엔테이션 에스티메이션인데 영어 학생 질문을 바로 넘어가 보면 그 도미넌트 오리엔테이션 어떻게 찾냐면 뭐 많은 방법이 있겠죠. 근데 가장 간단한 건 이런 걸 거예요. 뭐 만약에 막 내 주변부에 이 점을 주변으로 패치들이랑 이 주변으로 점들이 막 이렇게 스트럭처가 이렇게 있고 얘는 이렇게 있으면 각 점들의 그레디언트의 오리엔테이션 그냥 그 이미지 그레디언트 오리엔테이션이에요. 오리엔테이션들 보면 얘는 이쪽 방향, 얘는 이쪽 방향일 거예요. 그렇죠? 그럼 얘 도미넌트를 일로 놓고 얘는 도미넌트 일로 놓으면 이 두 개가 정확하게 이렇게 잡고 이렇게 잡으면 정확하게 디스크리션이 똑같이 될 거예요. 그걸 얻고 싶은 거예요. 그걸 할 수 있는 방법이 이미지의 그 각 픽셀의 그레디언트의 오리엔테이션에서의 맥시멈 도미넌트한 얘로 갈 거면 시프트였는데 그렇게 해도 충분히 잘 됐지만 핸드크래프트이니 러너블하게 가고 싶었던 게 아까 말한 방법인데 여러분 이렇게 질문이 많은데 질문을 안 했어요. 이건 방법인데 어떻게 러너블 할 거냐 결국에 뭐냐면 이 패치의 도미넌트한 오리엔테이션이 어딘지를 GT로 주면 끝나겠죠. 그렇죠? 그 GT를 가지고 그냥 네트워크에 넣고 학습을 시켜버리면 끝나겠죠. 그렇죠? 근데 그렇게 못하니까 어떻게 할 거냐면 이 두 개의 패치에다가 뭔가 오리엔테이션 네트워크를 줘요. 그럼 뭐 CNN이겠죠 그냥. CNN을 해가지고 이 패치의 오리엔테이션은 뭐 0부터 360도 중에 어떤 도로 나온다라고 아웃풋을 내뱉어요. 근데 그 GT가 없어요. GT가 있으면 넣으면 끝나죠. GT가 없어요. 그 어떻게 할 거냐면은 그 에스티메이션을 가지고 이 패치를 돌려서 그러니까 같은 방향을 보게 돌리면 그리고 피처 벡터를 뽑아서 얘를 시밀러하도록 가면 그쵸? 이 오리엔테이션이 잘 찾아졌어야 이게 더 시밀러하게 나오겠죠. 그럼 그거를 시밀러이드로 백프로브 시키면 이 오리엔테이션은 돌렸을 때 방향이 같아지도록 학습이 된다. 라고 하는 오리엔테이션 에스티메이션을 러너블하게 푸는 방법이었고 그 방법이 사실 여기와 완벽하게 똑같아요. 그래서 왜냐면 똑같은 저자가 썼거든요. 이 논문을. 지금 그 UBS에 있는 한국 분이세요. 네, 이광무 교수님이라는 분이 쓰신 논문인데 요 파트가 딱 요거랑 완벽하게 똑같은 부분을 이해해 주시면 돼요. 그래서 이 로테이션에 해당하는 그러니까 오리엔테이션에 해당하는 GT를 주지 않아도 이렇게 셀프 슈퍼바이 러닝으로 써봅시다. 셀프 슈브로 학습시킬 수가 있다. 라고 하는 개념인 거예요. 됐죠? 시트 결과나 오리엔테이션 반응이 영락생이 너무 좋은데 그 엣지의 방향으로 나오는 게 제일 정확하다고 하는 게 시프트의 아이디어였고요. 충분히 잘 나왔었죠. 근데 물론 그러한 가정이 깨지는 경우가 너무 많았기 때문에 시프트의 성능이 제한적이었던 거고 이 러너블하게 갔을 때 이미지의 이 주변 컨텍스트만 보고 메인한 디렉션이 어딘지만 찾아낼 수 러닝으로 찾아낼 수 있다면 훨씬 더 베스트겠죠. 그렇죠? 그래서 이제 이런 리프트나 이런 논문들이 나왔던 거고. 알겠죠? 자, 어렵구나. 그 사실 우리 그 수업에 다른 논문이 너무 많기도 하고 사실 뭐 저도 이 모든 논문들의 디테일까지 다 여러분들이 알기를 사실 원하지도 알면 좋죠. 근데 이 수업에서 다 알기도 쉽지 않을 거고 그래서 제가 조금 중요한 페이퍼들 그래도 여러분이 꼭 아는 페이퍼들은 이제 제가 언급을 해줄게요. 뭐 실제 뭐 실험에 나오는 거나 이런 거는 그러면서 중간중간에 제가 보여주는 페이퍼들은 그래도 이런 논문들이 의미가 있었다라고 하는 걸 보여주는 거고 혹시 관심 있는 친구들은 그냥 그 놈을 찾아보면 돼요. 너무너무 스트레스 받지 말고 그냥 제가 좀 강조했던 페이퍼들을 좀 자세히 공부를 한다라고 이해를 해주시면 감사하겠습니다. 알겠죠? Another question. 뭐 이런 숏포인트 이런 것도 너무 의미 있는 페이퍼였고 뭐 진짜 네 지금까지도 많이 쓰는 논문이긴 하지만 또 이것도 설명을 하면 너무 길기 때문에 제가 좀 넘어가는 면이 있어서 혹시 뭐 관심 있는 친구들은 찾아보되 제가 이렇게 설명을 깊게 안 한 논문들이나 어떤 모듈들은 너무 스트레스 안 받으셔도 돼요. 그렇죠? 여러분들이 충분히 혼자 공부하셔도 알 수 있는 내용이고 전체 흐름을 이해하는데 큰 문제가 없기 때문에 제가 설명하는 거라 주시면 되고요. 네. Any other question? Any other question from the foreigner student? No? 네. 조금 더 해볼게요. 그러면. So far, we discussed given two images, we discussed the detection. It's not object detection, 이런 local feature detection이에요. Feature detection and description. Measures lead selector가 뭐, for example, oriented estimation 같은 건데 그냥 뭐 이렇게 쓰는 거예요. 그냥 필요 없고, detection, description, and matching까지만 얘기를 하고 있어요. 그렇죠? And then one of the most important part is Landsat, but we did not discuss this one yet. But here, matching and filtering part, how can I find out the matching or correspondence given an n by m feature vector? N by m feature vector. One of the simplest one is nearest neighbor. 그렇죠? Nearest neighbor. There are three key points from the image 1 and 4 key points from the image 2 and find out nearest one. 그렇죠? Of course, we can consider advanced strategy. For example, mutually nearest neighbor strategy. What is that? If among the this one, among these four kinds of things, if this one is the this one is the top one, given these four kinds of things, and given this one, if we consider these three kinds of one, if this similarity between this one and this one is the most similar than these two one, then we can say that these two points are mutually nearest neighbor. So mutual nearest neighbor have to consider the consistent matching field comparing to just this nearest neighbor structures. In terms of these kinds of things, 잠깐만요. 넘어갈게요. So there was another direction to consider the to optimize the matching field. What does it mean? Right. Okay. Given this n by m feature vector, then this is our goal, objective, and in this paper, super cool. First of all, we just measure the inter and intra similarity between the feature vector. Looks like this. Blah blah blah. This is going to be the graph, and by convolving this graph with the convolution graph neural network, and update the graph here, and find out the node. This one and this one and this one. Then we achieve the consistent matches. Consistent means if this one matches to this one, the nearby other pixels, this one should not match it to this one in general, because in natural images the matches should be consistent, right? So by using the loss function, we can train the graph neural network to optimize the initial graph model. 그래서 이제 뭐 하는 거냐면 그냥 얘가 뭐예요? 아까 계속 n by d와 n by d가 나왔을 때 이걸 그냥 시뮬레이터로 계산해보면 n by m이 나와서 그냥 그걸 쭉 찾으면 되는데 그럼 너무 노이즈할 거예요. 그러니까 인디펜던트리 컨시더 하는 게 아니라 이렇게 얘네들 간의 각각의 시밀러 탭을 먼저 만들어 놓으면 얘가 그래프가 되겠죠. 이렇게 그래프 뉴럴 네트워크 같은 걸로 옵티마이즈를 해서 조금 더 얘네들의 시밀러리티, 그러니까 주변부의 시밀러리티를 보면서 업데이터 되게 해서 이렇게 매칭을 찾자라고 하는 연구들이 나왔고, 슈퍼글루라고 하는 방법도 있었고요. 넘어갈게요. 관심 있는 친구들을 찾아봐요. And yeah, there was a superglue. And but in 2021, there was a very interesting paper, image matching across the wide baseline from paper to practice. This is very long paper with 30 pages maybe. And this is the first figure here. This result was very interesting. I will read this one and let me introduce this one later. Every paper claims to outperform the set art. So it is possible or an artifact of insufficient validation. On the left side, we show serial matching obtained by D2Net in 2019, a state of art local feature using OpenCV, Landsat, blah blah blah, and we colored the inlier in graph with the nearly matched point, and red line means outlier. And on the right, we show the shift in 1999 with a carefully tuned MGSAC. Notice how the later performed much better. So even though there was the 20-year gaps, 그렇죠? 20 years gap. So what does it mean? This illustrate our take-home message to collectively evaluate method's performance. It needs to be embedded within the pipeline used to solve the given problem, and the different components inside pipeline need to be tuned carefully and jointly, which require enduring the domain expertise. So this paper proposed some benchmark and the evaluation protocol, blah 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 blah. But from this figure, we can say that even though there was the 20-year improvement, given the same sharing, I mean the pair sharing, we cannot say learning-based method always outperform handcrafted method. Why? There are so many kinds of reasons, because the learning-based method very sensitive to the domain gap or the stuck in the local minimum or the what else? Some kinds of overfitting problem given the training data like this. So we can say that the learning-based method does not always outperform handcraft one or the previous method. So this shows the very interesting. It shows it proves the very interesting method. And in other words, we have to consider traditional one or the previous SOTA to achieve the domain knowledge, in this case, the matching knowledge, domain knowledge, to formulate your new model. 자, 그래서 이제 뭐 설명했죠. 그래서 그러니까 10드라고 한 페이퍼랑 이제 D2는 아까 뒤에 제가 얘기했던 것처럼 20년 가까운 세월이 흘렀어요. 그렇죠? 20년 가까운 세월이 흘렀음에도 완벽하게 동일한 세팅으로 놓고 실험을 해보니 아직까지도 오히려 10드라는 페이퍼가 더 잘 나오더라 라는 걸 이제 증명을 해야죠. 그러니까 무슨 의미를 갖는 거냐, 어쨌든 러닝 기반 방법들이 무조건 좋은 게 아니고 뭐 오버피팅 프로블럼, 도메인 갭 또는 뭐 많은 문제들에 의해서 어떤 세팅들에서 오히려 아직도 핸드크래프트 방법, 러닝이 아닌 방법들이 더 잘 나오는 경우도 많더라 라고 하는 메시지를 던져줬던 거고요. 다시 얘기를 하면은 러닝이 무조건 안 좋다라는 게 아니라 단순히 우리가 정답 때려넣고 학습제 때려넣고 우리 네트워크를 열심히 학습시켜서 문제 틱 풀었어요가 아니라 그 도메인 필드, 그러니까 매칭이라는 필드죠. 여기서는 도메인 필드에서 수없이 몇십 년 동안 연구됐던 그런 도메인 나레지들을 내 네트워크에 잘 녹여내는 게 정말 중요한 이슈다 라는 걸 보여줬던 메시지죠. 저는 이제 우리 학생들이랑 항상 얘기할 때 그런 연구를 우리가 한다고 하는 것이 결국에 뭐 어떠한 진리, 여기 학생은 좀 미안한데 진리라고 하는 거로 다가가는 거라고 생각했을 때 결국에 이 진리로 가는 과정을 저는 진리의 파편이라고 많이 표현을 하거든요. 진리의 파편들. 그러니까 그러한 진리. 여기서 이미지 매칭이 잘 돼야 되는 진리는 있을 거예요. 아직 발견되지 않은 부분들 아니면 발견된 부분 많은 진리들. 결국에 옵티멀한 매칭이 가야 되는 그 진리를 도달하기 위해서 수많은 논문들, 20년에 가까운 논문들이 파편들을 쏟아내고 있었던 거죠. 그 파편들을 가지고 진리에 도달하는 과정. 사실 그게 저는 연구라고 생각을 하거든요. 여러분들이 이 논문을 보면서 조금 많은 생각을 해봤으면 좋겠어요. 그래서 좀 가져와 봤고. Of course, very recently, after 2021, there was the image matching with transformer. 그렇죠? Transformer change everything. 그렇죠? Image matching with transformer. 어렵네요. 그렇죠? 할까요? 이거를 해야 되나? So main ideas like that. I will briefly mention this one. Main ideas like that. First of all, extract the two feature vector from the image 1 and image 2, image A and image B, and flatten this feature vector and aggregate this feature vector with self-attention and cross-attention in transformer to find out similarity between these two feature vectors. I will skip this one, but and train this transformer to maximally find out the corresponding point here. This is the loft paper. This is called the lofter. And this is a lizard. As you can see here, there are so many homogeneous lesion and taxoless lesion, but this lofter find out good inlier. So looks like this. It's very, very interesting, right? So this kind of output can be used the AR or the 3D construction or the visual localization models. 이런 데 많이 쓸 수 있다. 거고요. And there was another paper which was called the COTR, Correspondence Transformer. And we'll skip this one later. We'll skip this one. And let's check the paper if you are interested in. Yeah. That's it. So far, we discussed the sparse matching point. In other words, this is the sparse optical flow. Sparse optical flow. But sparse optical flow means, okay, given two images, this is a video, so frame by frame, we just find out how to find out sparsely detected point matching, right? But in many cases, we require to extract dense optical flow. 그런데 매칭을 합시다. Sparse matching and dense matching. Or sparse correspondence and dense correspondence. Looks like this. So, dense correspondence estimate the flow or the matching of whole pixels in the images. Compared to the previous paper that considered the few featured point. So this is a dense correspondence. Why? Why do we have to know dense correspondence? So there are several kinds of applications that require the dense correspondence. Stereo matching and optical flow is one of them. Stereo matching or the optical flow aims to establish pixel level correspondences between the visually similar images that is taken under similar viewpoint, stereo matching, and similar time optical flow. For example, The stereo matching is to estimate the depth information from the left images and right images with a two different camera in a stereo setting to resemble your eyes. And to find out this kind of 3D depth map, we require to solve. We have to necessarily solve stereo matching problem. And optical flow means the motion information to achieve the motion information from between current frame or previous frame. It looks like this. This is overlaid images, and this is optical flow or motion estimation or the motion information. So stereo matching and optical flow is one of the most popularly studied area. So this kind of problem can be categorized as a test correspondence. Why? There are so many kinds of applications. Stereo matching can be used in many autonomous driving systems, or the 3D construction, or 3D object detection, things like this. And optical flow also can be used in intelligent transportation system, or object tracking, or action recognition, because this optical flow contain or consider the motion information. Right? So these two kinds of things application for the test correspondence. Okay, question. 자, 뭐 여긴 쉽죠? 그래서 뭐 지금까지 쭉 스펄스 매칭을 해오다가 보니까 사실은 이런 댄스 모든 픽셀들의 매칭을 다 찾아내는 문제들이 나오기 시작하죠. 이런 경우 스테레오 매칭이나 optical flow. 스테레오 매칭 같은 건 뭐냐? 레프트 영상과 라이트 영상을 찍어서 두 영상 간의 어떤 대응점을 찾아서 그 대응점으로 어떤 픽셀 단위로 정의되는 3D 정보를 찾는다거나 픽셀 단위로 정의되는 이런 모션 정보를 찾는 뭐 이런 데 다 쓰이는 이런 데에서 이제 이렇게 픽셀 단위의 매칭을 찾는 문제가 나온다라는 거죠. Question. 여기까지 어렵지 않죠? No? Okay, so let's take a 10-minute break. Let's continue 3:55. 우리 오늘 조금 진도가 생각했던 것보다 좀 늦어지고 있긴 한데 괜찮아요. 다음 주도 있으니까 조금만 10분 쉬었다가 우리 다시 한번 해봅시다. Okay, sorry for late. Yeah. Okay, so question. Is there any already data on which we know? No, not yet. Okay. Maybe June, maybe, but the date is not finalized yet. Any question? Okay, let's continue the deep dance correspondence. So we move to the dance correspondence. So in fact, the dance correspondence pipeline is similar to the sparse local matching pipeline. What was the feature detection, feature description, and matching, right? Similarly, dance correspondence requires the feature description part because this is the dance matching problem, so we don't need to extract the feature vector, because we have to consider all the point. So we directly consider the feature description part. So the question is how to describe the local patch effectively and efficiently. For example, the general local feature, the similarity measure, learned feature vector, something like this. So this is the research point or the research topic in the local feature description. And in dance correspondence, we have the one more pipeline, one more part, correspondence regularization or co-optimization. So the question is how to regulate or the optimize the correspondence field. We'll discuss this one later. Anyway, so dance correspondence consists of feature descriptor representation and correspondence regularization. So first of all, what is a good local feature descriptor? What is the good feature local feature descriptor? So given input images, image 1 and image 2, we can extract a feature vector from each pixel. Okay? So good feature descriptor, the good feature vector looks like this, should be here. So in a feature, some feature space, good feature descriptor should be robust and distinctiveness. So robustness means matched patches should generate same or similar feature vector, while non-matched patches should be different feature vector. So in feature space, good feature space should be here or here. Robustness and distinctiveness. And that's great from the pipeline consisting of the feature extraction and regularization, right? So feature extraction, how to extract a feature vector, very similar to the local feature matching, as we discussed deep disk or something like this. First of all, we extract the feature vector and find out the similarity here. So it's going to be matching. But in regularization step or optimization step, we consider the nearby pixels for the point, nearby pixel, and just to give the regularization. What does it mean? If we consider here, and if this point gives a matching here, and this point matches given here, then this point should be similar to the nearby pixel, looks like this. Then the question is how to define the nearby pixel and how to measure the similarity between the nearby pixel and how to formulate this kind of the regularization or the smoothness is the key design factor. But anyway, that correspondence method required this regularization step. So feature description, a feature extraction step and regularization step. So anyway, even though any kinds of dense correspondence method can be developed, but most of the problem or most of the method contained categorized one of them, and most papers or the method should be described in feature extraction manner and regularization manner. So in other words, we have to mention that if we have the one method, what kind of feature extraction method is used and what kind of regularization technique is used in the method, in given method. This is a dense correspondence pipeline. So yeah, we will move to this one. We'll skip this one. Okay, I want to start with the case study from the stereo match. So what is the stereo matching? To discuss stereo matching, we have to consider the stereo setting. So given a scene, we want to make a machine that resemble our two eyes, our human eyes. So similar to human eyes, we use the two camera, left camera and right camera, known camera. Find the relative depth. Known camera means known camera pose. And find the relative depth between left images and right images. And correspondences between left image and right images give us depth information, 3D information. That's a stereo match. So stereo match means given two images from the different viewpoint. So different viewpoint was like this. How can we compute the depth of each point in the images? How can we compute the depth or disparity or 3D information of each pixel in the images based on how much each pixel moves between two images, left image and right image. This is the stereo match problem. So if we extend this two-view stereo matching to the multi-view stereo setting, looks like this. It's going to be multi-view stereo. And all of this one based on the epipolar geometry constraint. So what does it mean? Looks like this. Image one, given image one is left images, image two is right images. Given image one and image two, this is the real 3 point, and let's consider the point P in image one. And epipolar constraint mean if we search this line in the input image 2, then find the same point, then by considering the line, this one line and this line, we can find out depth of this point or the 3D position by only considering the image 1 and image 2 and image left hand image and right images. So this is the epipolar geometry. This plane is called epipolar plane, and this line means epipolar line. So this epipolar geometry of a two-view is described by very special matrix, a special 3x3 matrix, which is called the fundamental matrix. F maps the homogeneous point. Let's just skip. Point in the image to the line to the image 2. This epiphone line image 2 of point P is F of P. This one. This is very, very difficult, but please just remember, if we can find out correspondence between pixel P and pixel P among this epiphone, then we can recover the 3D information. This is the main strategy of the stereo match. 자, 이해했죠? 그래서 에피폴 지오메트리, 여러분들 아마 혹시 3D 관련된 일을 하는 친구들은 모르겠네. 여기 혹시 뭐예요? 혹시 우리 그래픽스 하는 친구들이나 좀 다른 필드에 갔던 친구들은 조금 익숙한 얘기일 수도 있고, 좀 다른 친구들 왔던 친구들은 조금 어색할 얘기일 수도 있는데, 에피폴 지오메트리라고 하는 게 좀 중요한 이슈죠. 그렇죠? 에피폴 지오메트리라고 하는 게 결국에 3D를 리컨을 어떻게 매칭을 하느냐에 관한 얘기예요. 그렇죠? 무슨 얘기냐면은 이렇게 봅시다. 여러분들은 3차원을 인식할 수 있는 이유는 여러분들 눈이 두 개가 있기 때문이에요. 그렇죠? 왼쪽 눈과 오른쪽 눈. 자, 오른쪽 눈을 맞고 왼쪽 눈을 한번 보고 왼쪽 눈을 맞고 오른쪽 눈을 한번 봐봐요. 그 영상이 두 장이 나오거든요, 여러분한테. 근데 보면 동일한 포인트가 다르게 찍혀요. 가까울수록 차이가 많이 나고 멀수록 차이가 거의 없어요. 변이차라고 하는 거예요. 그렇죠? 결국에 이 에피폴 지오메트리 여기서 나타나는 현상인데 무슨 얘기냐면 이미지 원에서 어떤 P라는 점을 그렇죠? 이 점을 봤을 때 어떤 한 점을 봤을 때 진짜 3D 월드에 있는 한 점을 봤을 때 이미지 원에서 이 P라는 점에 찍혔으면 그 점이 이미지 2에 어디 나타날까에 관한 얘기인 거예요. 근데 그 이미지 2에 어디 나타날까가 결국 얘의 뎁스, 얘가 얼마나 떨어져 있느냐와 연관이 되어 있을 거고, 그렇죠? 이게 Q라는 점이 나타날 거면 그러면은 결국에 보면은 이 Q라는 나타나 자체가 여기랑 만나야 되니 이 뎁스가 이만큼이다. 이 플레인 안에 나타난다라고 하는 컨스트레인이고, 그 Q는 결국에 이 플레인, 이 Q는 결국 이 이미지 1과 이미지 2 사이의 어떤 카메라 포즈에 관련되는 이 펀더멘털 매트릭스, 카메라 포즈에 관련되는 펀더멘털 매트릭스에 의해서 이 에피폴 라인이라는 게 결정나고, 이 에피폴 라인 안에서 있는 점들 중에 P와 가장 유사한 점을 찾아내면 바로 이 에피폴 컨스트레인 때문에 이 3D 정보를 찾을 수 있다 라고 하는 게 결국 에피폴 지오메트리고, 스테레오 매칭 하시면 뭐냐, 이 P라는 점과 이 에피폴 라인에 있는 모든 점들을 비교해서 가장 시밀러한 Q를 찾아내는 과정이 바로 이 스테레오 매칭, 그걸 모든 픽셀에 대해서 했을 때가 바로 이 스테레오 매칭이라고 할 수 있는 거예요. 어렵죠? 어려워요, 여러분? 어때요? 이해돼요? 어려울 것 같은데? 자, 이해되는 사람, 내 방금 말한 거, 에피폴 지오메트리. 좀 더 가봅시다. 이해 안 되면 좀 얘기해줘요. F가 4바 이상. 정학생 좀 깊게 들어갔는데 엄밀히 가면 4바 이상으로도 설계할 수 있고 3바 이상으로도 설계할 수 있어요. 그렇죠? 그러니까 호모제너스 코딩을 생각하느냐 아니냐에 따라서 좀 이 매트릭스의 크기가 바뀌긴 하는데 그냥 정학생이 생각하는 그 펀더멘털 매트릭스랑 똑같다고 이해해도 돼요. 지금 이게 사실은 이 매칭 파트이기 때문에 요 얘기는 사실 3D 때 조금 더 제가 자세히 설명할 건데 일단은 그냥 전학생이 이해하고 있는 펀더멘털 매트릭스라고 이해해 주시면 돼요. 맞죠? So, in other words, the stereo matching aims to given one point in left images. Here's left, right. x1, y1 on epipolar line. We want to find the corresponding pixel x2, y1 because there's no difference in y-axis because this is a stereo match problem. So epipolar line is built to the x direction only. So there is no two images captured by purely horizontal translated camera rectifies stereo pair. So if we will set up the stereo camera, left camera, right camera, there's no translation but horizontally, vertically. So pure horizontal translation happen. So term matching, find the correspondence between two pixels. It means that how can we measure the similarity between 2 points? We can't do that, right? So to measure the similarity, we have to consider the local region of these 2 pixels, or this local region, or this local region, blah, blah, blah. And it means that measure the similarity between images and pick the best, which will be the disparity or the best information. That's the term matching. So your basic term matching algorithm should be looks like this. For each epipoline, for each pixels in the wrapped images, and compare every pixels on the same epipoline in the right images for this pixel, compare all the pixel, and pick pixel with a minimum matching cost. So how can we do that? Consider the local region and measure the similarity for all possible pairs and pick the best. Pick the best. This is stereo matching. It means that you require better patch similarity technique. In other words, this is a patch-based cost computation. So for every pixels in the left images, create the tiles and compute the cost for the disparity, then move to the next tile. So it means that this is the left images and this is the right images, and this pixel, this pixel move to here. But this pixel almost the same. So this one, how much move means related to the depth information. So this is the disparity map. So this translation in x-axis. So this is the disparity map and patch-based cost computation method. So how to measure the similarity? This is one of the most important questions, right? How to measure the similarity? What's that? This is the same question in the local feature matching, right? Local feature matching. What's that? For example, deep compare, deep disk, blah blah blah. So how to measure similarity? So traditionally, some of absolute different and some of scale different, blah 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 blah. So this kind of handcraft method was used, but nowadays you can easily spec team learning based method. The team learning based similarity technique. Maybe the good, maybe the alternative. So maybe the good solution for the to measure the similarity in the stereo matching pipeline. Yeah. How to pick the good patches? Maybe we can consider the patch size, various patch size, multiple size, and weight contribution neighboring pixels. But nowadays we consider the deep neural network. But only approaches considering the handcrafted similarity method, something like the SAD or census transform or the NCE. This is very specific. If we have two patches, 1, 3, 2, 3, blah blah blah, and 2, 3, blah blah blah, then some of the absolute difference mean difference between pixel value and summation. This is some of this is very very simple way to measure the similarity between two patches. But that apparently really can suffer from results by those kind of technique can suffer from the noise, foreground flattening, blah blah blah. Why? Homogeneous lesion or the repeated structure, occlusion, patch sensitivity. Occlusion is one of the most important issues in stereo match. Why? if you consider the same people in left images and right images, due to the geometry constraint, this region and 아니죠, 잠깐만. 아니다. This region and this region may be occlusion. It means that this region only appear in either left image or right images. 맞죠? 그러니까 오클루전이 왜 생기냐면은 우리가 지금 보면 아까 디스패리티 때문에 그러니까 움직이는 정도가 커지니까 결국에 내가 어떤 포그라운드, 그러니까 앞에 있는 오브젝트가 왼쪽으로 볼 때, 오른쪽 볼 때 그 오브젝트가 보여지는 그 시점에 따라서 이 배경 부분이 가려지죠. 가려지는 정도가 달라지죠. 그렇죠? 그게 이제 바로 오클루전인데 이제 그런 문제 때문에 기존에 핸드크래프트 방법들이 안 된다라고 하는 얘기를 하고 있는 거고요. So learning to compare the matching cost is maybe the natural direction, right? So from the one of the left image patches and on the right image patches, we extract the picture vector and compute the similarity. So this is the MCCNF path, which is the very, very similar to the deep compare, deep disk, right? And this paper, MCCNF upgrade version, proposed another architecture from left patches and right patches, extract the conversion feature vector and use the additional fully connected network to directly measure the similarity, not a dot product. This is similar to the decompare method, but this paper used the stereo matching in JMNLR, Journal of the Machine Learning, 그렇죠? Journal of Machine Learning in 2016. At the time, this kind of technique achieved the state of art. Look at this. So this is the left images, and this is the right images, and this is the ground truth. Even though this is the dense match problem, in real world, we cannot make a dense ground truth. Why? There's no way to measure the real depth for each pixel. But instead, by using the hardware like LiDAR, we can achieve sparsely sampled depth information here. So instead of matching in deep learning area, we use this sparse depth point to train dense correspondence network. Okay. And we measure your dense correspondence network, stereo match network, in sparsely annotated samples here, because there's no way to generate real dense 3D information. Anyway, comparing to the census handcraft method, MCCN의 past version 이거 and MCCN correct version here generate the very, very good depth information with error rate. Looks at this. So this is the MCCNN learning to compare the matching cost in the stereo matching. And of course, there was so many kinds of variants, MCNN variant, SWCNN, FEN, or blah, blah, blah. There was some kind of variant. But the main idea or main philosophy started from this paper, MCCNN paper, in stereo matching field. Question? No? Okay, because today we discussed so many kinds of concepts, almost 80 slides. We will stop here and we'll move to the next topic, optical flow, next week. Before that, please recap what we've done so far, because I will upload today's recorded video to our YouTube channel, please recap. If you don't understand what I mean, please recap and let's move to the next topic. And okay, and then in next lecture we will see the stunt presentation. So if you didn't present yet, and if you want to present more, please apply on our Google Sheet, and I will let you know. I will announce the presenter tomorrow. Okay, tomorrow night. So, 아마 이제 여러분 말했지만 발표할 게 몇 번 안 남았죠. 우리 이제 기말고사 해봤자 몇 개 안 남았는데 아직 발표 안 한 친구들, 그리고 본인 중간고사 너무너무 못 봤다 하는 친구들 만회해야 될 테니까 꼭 지원해 주길 바라고요. 아마 여러분 조금 어려운 내용일 수도 있을 수도 있겠는데, 오늘 이제 쭉 보다 보면 알겠지만 너무나 중요한 얘기고, 내가 컴퓨터 비전의 역사에서 빼먹으면 안 되는 분야가 바로 이 비주얼 코레스폰던스라고 하는 분야인 것 같아요. 그렇죠? 그렇기 때문에 꼭 복습해보고요. 모르는 거 있으면 저한테 물어보시고 우리는 다음 주에 보도록 합시다. Question? No? Okay, so this is end of this lecture, and this is end of stereo matching part. Thank you very much, and see you next week. 오늘도 수고하셨습니다.
죄송한데요. 질문이 한 가지 있는데요. 가셨나요?
정은 학생 질문해도 돼요.
네네네. 지금 스테레오 매칭에서 결국에 약간 하고 싶은 게 덱스 정보를 잘 에스티메이션 하는 게 맞는 건가요?
맞아요. 그러니까 스테레오 매칭 하고 싶은 거는 딱 이걸 하고 싶은 거예요. 어떤 레프트 이미지가 있을 때 요거의 깊이 정보. 그 지금 보면 이게 칼라를 입힌 거는 사실은 그냥 1D예요. 그러니까 그레이스케일 밸류인데 이거를 그냥 눈에 보게 좋게 하려고 이렇게 어디 있더라? 이렇게 그냥 칼라를 먹인 것 뿐이거든요. 그래서 이게 밝을수록 가까이 있다, 멀수록 이렇게 어두워진 색깔을 표현하는 거가 딱 스테레오 매칭 하고 싶은 거죠.
그래서 궁금했던 게 저희가 시중에 파는 스테레오 카메라들이 많잖아요.
그죠.
네, 여기서 좀 의아했던 부분이 라이다랑 오차가 한 4%, 센서스는 4%, 그리고 MCCNN은 2, 3% 이런 식으로라고 나와 있었는데, 그 말은 무슨 저희가 시중에서 사는 스테레오 카메라들이 오차가 그래도 한 5% 이상이다라고 생각을 해야 되는 거니까.
어떤 카메라를 쓰냐에 따라 달라지긴 하는데 애매하죠. 그러니까 어떤 데이터셋에 했느냐에 따라 5%다라고 하는 게 좀 애매한데 기본적으로 그러니까 우리가 그냥 뎁스를 언어에 치면은 기본적으로 그러니까 인도어 씬, 우리가 만약 정학생 같은 로보틱스에 있으니까 만약에 내가 인도어에서 뎁스를 언어에 치면 사실 센서를 얻을 수가 있어요. 그렇죠? TOF 같은 센서로. 그렇죠? 근데 이제 요 스테레오 매칭을 하는 이유는 사실 엄밀하게 아웃도어 씬을 위해서거든요. 그러니까 아웃도어에서는 TOF가 동작을 일단 안 하고 일루미네이션 때문에, 그렇기 때문에 가능한 경우가 이제 라이다밖에 없죠. 그렇죠? 근데 아까 라이다는 얘기했지만 너무 고가기도 하고 뭐라고 하죠? 포인트가 찍히는 게 사실 스팔스하게 찍힐 수밖에 없죠. 그렇기 때문에 우리가 생각할 수 있는 건 스테레오 매칭으로 찾아내는 이러한 뎁스 맵일 수밖에 없는데, 첫 번째가 말했지만 이러한 뎁스 맵에 그라운드 트루스가 없어요. 그렇죠? 만들 수가 없죠. 그러니까 리얼 아웃도어 씬에서의 리얼 댄스한 3D 정보는 얻을 수가 없기 때문에 일단 사실 매저 자체를 할 수가 없어요. 그렇죠? 그럴 때 그냥 비주얼리 더 잘 나온다라고 말할 수 있는 정도이고, 굳이 매저라면 아까 말했지만 이런 라이다 포인트 정도와 어느 정도 유사하냐 정도인데 사실 그것도 정확하지는 않고요, 사실. 그렇죠?
네네.
뭐라고 이해하면 돼요. 그리고 아마 시중에 파는 대부분의 스테레오 카메라들은 또 무거운 알고리즘을 못 써요. 이런 스테레오 알고리즘은 거기는 거의 실시간으로 나와야 되기 때문에, 그러니까 카메라가 돌아가면서 뎁스를 바로바로 뱉어줘야 되기 때문에 정말 셜로우한 방법들을 많이 썼거든요. 예전 방법들을.
아, 그래서 이제 그 멀리 있는 정보들은 뎁스를 잘 못 받는
맞아요, 맞아요. 예.
게 좀 있.
그러니까 멀리 있을수록 디스퍼리티가 작아지니까 매칭도 하기 힘들어지고 하니까 사실 찾기 훨씬 더 어려워지는 거죠. 근데 그래서 요즘 나온 스테레오 카메라들은 뭐 딥러닝 기술이 들어가는 게 있을 수도 있는데 사실 이게 좀 방향성 자체가 뭔가 스테레오 카메라에 대한 연구보다 사실 이런 스테레오 카메라의 뭐 하드웨어나 이런 연구들은 사실 조금 한 3, 4년 전 정말 3D가 좀 유행할 때 아바타 나오고 막 그때를 기점으로 사실 많이 연구가 됐고 스테레오 카메라 자체를 사실 많이 그렇게 만드는 것 같지 않아요. 그래서 제 말은 요즘 스테레오 카메라들이 정말 소타 여기 좀 넣고 막 이렇게 하는 것보다는 제가 이제 3D 시간에 좀 얘기하겠지만 요즘에 오히려 싱글 카메라를 가지고도 3D를 더 자세히 할 수 있는 솔루션들에 대한 거가 조금 상업적으로 더 가치가 있고 또 관심이 있는 것 같아요. 개인적인 생각으로.
네, 감사합니다.
네, 알겠습니다. 혹시 뭐 다른 친구들 의견 없으면은 네, 오늘 여기서 끝냅시다. 그럼 고생하셨습니다.